Hi, everyone. For today's lesson, we're going to focus on something really important. We're digging into vectors. Now, vectors is the most powerful tool we're going to be using in the course this year, and it's something that's going to come up over and over and over again. We're going to use it in kinematics for looking at motion. We're going to use it in dynamics to look at forces. We're going to use it in fields when we're looking at electric and magnetic fields. It's just something that's going to keep coming up over and over and over again. We're going to use it with momentum when we look at momentum and collisions. So vectors is something that we really want to build strong skills at, and so we're going to start from a nice base level and we're going to build those skills and then we're going to use it again and again. If you find that you're struggling with this topic, it's really important that you spend some time with it and you seek some support from me and anywhere else you have support from in order to build your skills so that you're going to have a really successful rest of the semester. Okay, let's jump in and talk about vectors. First of all, vectors, as we've talked about before, are things that have magnitude and direction. That means they have an amount and a direction. We're going to use them for lots of stuff like I just mentioned: displacement, velocity, acceleration, force, momentum, gravitational electric fields, and more, more, more. They keep coming up over and over and over again. So in diagrams, when we draw vectors, we're going to draw them as arrows, right? Straight arrows. And the length of the arrow is going to represent the magnitude of the vector. Longer arrow means more magnitude. For the example of force, longer arrow means more force. For velocity, longer arrow means higher velocity. The direction, of course, is going to point in the direction that the vector goes. So let's first look at a couple of examples. Now, I've had you watch a video describing these, and so hopefully you've checked that out. And I've said here, let's label the directions two ways: a true bearing and a quadrant bearing. Now, I'll also mention there is another way here that's mentioned. It says, note some sources put the angle first, like 42 degrees east of north. You'll find this in textbooks that are a little bit older. It's kind of fallen out of favor now, but you will find sources that describe it like this, including some of the videos I'm going to have you watch by the Flipping Physics channel by a gentleman named Mr. P. He writes his angles like this. So, if we were talking about north 42 degrees towards the east, another way of saying that is 42 degrees east of north. And those are equivalent to one another. I like the one that has the angle in the middle and the directions on either side. And so that's the one I'm going to use, but you will see others. Okay, so we want to have our true bearing and our quadrant bearing. Now, probably we can label this, right, with north, south, east, and west. If we're looking from above, that's a common way that we're going to see these, and how we're going to describe motion. Never, never eat shredded wheat is how they used to teach me how to remember that one. Okay, so we're going to say, first of all, we could describe this angle a couple of ways. We could look, say, from the east, we're going to the west. So we could describe this as putting a square bracket around it: east 70 degrees towards the south, rather, sorry, not west, east 70 degrees towards the south. Another way to describe that is the one the video mentions is preferred. To me, I don't really care. They're both fine. But we know there's 90 degrees between south and east. We could describe this as south 20 degrees towards the east. Those are equivalent to one another. Those are describing the same angle, right? We could also, though, do our true bearing. I'll do this one in red. And we could start here at north, go all the way around until we hit our vector. And we say, okay, north to east, that's 90 degrees, and plus another 70 is a total of 160. So we just write it like this: 160 degrees. And by putting square brackets around it, we know we're talking about a direction. In like aviation and stuff like this is how directions are described. You start with north as your zero, and then you go clockwise from north. And so all you need is that one number, and it's going to tell you. So that is another common way to write these, and I'll use both of them so that you can kind of get used to using it interchangeably. Okay, similar to this one here, we start at north and go 50 degrees towards the east. So we'd say north 50 degrees towards the east. We could also describe it from the east if we wanted to. So say we start at the east and we say, okay, 50 plus 40 would make 90. So east 40 degrees towards the north. I'm fine with either of those. We could also describe its true bearing by starting here at 0 at north and going 50 degrees clockwise. This would be 50 degrees like that. Last one. If you haven't tried these on your own yet, try them first and pause the video and try them and then come back and see how we're doing. So this we could start at the west. That's pretty easy. And we'll say west 37 degrees towards the south. We could also start at the south, right? And so we'll say south, and we're going to go 53 degrees towards the west would be another way to do it. Now, if you want to do your true bearing, we could start at north and go all the way around, right? And for there, we say, okay, north to east is going to be 90, and then east to south is another 90, and then we've got to add 53 onto that. And so we're going to say that's 233 degrees to get all the way around to there. So those are different ways we could describe it. Now, for each of these, I could also have described them by saying, I'm going to take my east 70 north. I could have said 70 degrees, sorry, south of east. I could also have said that, and you will see these in certain places. This one I could have said 50 degrees east of north. And this one, I could have said 37 degrees south of west. I usually won't use those because I don't know, I find that kind of clunky, but that you'll see those around. Okay, let's jump on to our next one here. This is our next example, adding and subtracting vectors. Again, there's some videos I've asked you to watch in terms of how we're going to add and subtract vectors. But I want to take you through these examples. So again, try them first yourself. Just sketch them on some paper, and then check back here to see if we agree. Now, first of all, we're just going to say a plus b is our first. So remember the vectors. We've got some hints here. We always want to add vectors tip to tail. That means we start at the not pointy end, and then we go to the pointy end. That's how we're always going to add them. The other vector hint is to add a negative vector, just flip the direction, because we know the negative of a certain vector is the same magnitude going the opposite direction. That's one thing we know about vectors. So I can say, okay, if A is A, my example A is A plus B. So I'm going to grab my A vector here, and then I'm going to grab my B vector. I'm going to go tip to tail. So I'm going to put my B vector right here. And now I want to draw my resultant, right? So I can actually use my drawing tools here. Let's make these red because that'll look nice. I'm going to start at the beginning and draw my resultant right to the end here. And now if I want to describe that, I can actually write that as A plus B, like that. I want you to pay special attention to the fact that the vectors don't go in a loop, right? We don't go to like A, B, and then end up with the arrow back over here. That's not how this works. It doesn't create a full circuit, right? We're saying following A and then B and adding them together gets you to the same place as this red vector. So the two tails start at the same point and the tips end at the same point right here. Okay, so be cautious with that. I often see students wanting to create a full circuit and go, well, this vector goes here, and then this vector goes here, and then this vector must go over here. No, that's not correct. Okay, let's try our next one, B plus A. So here we go. Ooh, let's undo that. We're going to go B plus A. So here's our B, and here's our A, and we'll do it like that. Now, rather than redrawing that red vector, what I can do is I can just grab it here, and I can show you that, oh, would you look at that? A plus B and B plus A create the same vector. The result is the same. So those are equivalent to one another. That's the nice thing with vectors. As long as we preserve the sign in front of them, we can flip their order, no problem. Okay, let's try C here. I've got A minus C, so I'm going to get out an A, and I'm going to get out a C. Now I know it's minus C, and what do I do when I'm subtracting? I turn my vector around like that. So I'm going to go again, add them tip to tail like this. Okay. And now my resultant vector, if I go back to my pen here, it's going to look like this. I'm going to start here. I'm going to go up to here. Okay, so that one is going to be my A minus C. Now, I could also have written this. I could not write this as C minus A because that's not equivalent. I could write it like this, right? I could have A minus C equals A plus negative C. And then I could move the C to the front and I could say negative C plus A. So negative C plus A will actually work out the same. And we can see that if we grab a couple of them, we go, okay, here's C. I'm going to make it negative like that. And then I'm going to have an A and I'm going to add it on like that. And lo and behold, hey, looky here. This one is also equivalent. Look at that. Okay, let's try D here. 2A plus B minus 2C. Let's give this one a shot. So let's grab two A's first of all. I got an A, and I got another A. That's two of them. And then I got a plus a B. I'll add a B onto there. And then minus 2C. Okay, I've got two of them, and they're both negative. So I'm going to grab one, and I'm going to spin it around. And I'm going to grab another one, and I'm going to spin it around. Both of them want those going backwards. Okay, now we're going to add those on, right? So I'm going to go tip to tail. I'm going to put it right there. And the other one I'm going to put right here, like that. I follow the order, follow the line of the vectors. Now let's add our arrow on here. Our resultant vector, we call it, and we're going to draw it like that. That's our resultant vector. And let's write in what the resultant vector is. It's going to be a lot here, so I'm going to kind of write it sideways if I can. 2A plus B, excuse me, minus 2C. There we go. Okay, I was able to write it in. So there's my resultant vector from all of these vectors being added together. It's really important to understand that these are equivalent. This little red vector right here that I just drew is equal to all of these other black vectors that go all over the place when we add them together. Those two things are equal, which is kind of a little hard to wrap your brain around, right? We're used to linear mathematics, but we're dealing with vector addition here, and those things are equal to one another. How we can think about it is a series of forces. That's a nice way to think about it. If I have something and I'm pushing on it with the force of this red vector here, that is equivalent to all of these black vectors pushing on the same thing because they kind of like counteract one another to a degree. And when you add them all up, the overall force would be the same as the red vector. So thinking about them as forces is a nice way to understand how those would be equivalent to one another. They are equal to one another. Okay, when we're solving for addition or subtraction problems mathematically, we were just sketching there. Let's do it with some math. When we're solving for them in one or two dimensions, there's three possibilities that exist. You could do this in 3D, right? You can do vectors in 3D. There's lots of computer software to do that. Mathematically, you can do that. Um, it just is a lot more complicated. So we are going to stick to two-dimensional vectors because that is very useful, and that's the scope of what we're looking at. So we're going to look at three examples, okay? And these examples are going to work for all vector addition or subtraction problems. And it could be displacement, velocity, acceleration, force, momentum, electromagnetic fields, all that stuff. It's going to work for everything that we're going to, like almost everything we're going to study this year. You're going to see us coming back to this again and again. So in these examples, the three different cases, I'm not going to include units. And the reason is I want to keep them simple. I don't want to focus on units because it could be velocity, meters per second, could be acceleration, meters per second squared, could be force in newtons, could be momentum, which has more complicated units, a combination of units, could be displacement in meters, could be magnetic field in Teslas, like it could be any of those. So I'm not going to include units for the most part in these questions. I'm just going to include direction, and we're going to acknowledge that this would work for any of those. Okay, so here we go. Let's give this a try. Here's case one. One-dimensional linear situation. So it's a one-dimensional situation. Things go north and south, forward and back, up and down, left and right, and that's it, right? Only one dimension. So it can only go in the north or south, or it can only go in the forward or back. We're going to do sketch and find the resultant vector. Sketching is a nice way to start, right? And often we'll solve these problems for you in like pretty straightforward ways. So I'll say 10 north plus 12 south. Again, this could be um, a velocity. So it could be like a boat's motion and the current, or it could be forces, 10 newtons north and 12 newtons south, right? So we're going to say, okay, if we start here and there's a vector that is 10 north, I'll draw north up like that. That's going to take me to there. And then the 12 south is going to take me down to there. I say, what's my resultant? Well, I started here and I ended down here. So that's my resultant like that. And you'd say, what is it? Well, 10 north and 12 south. That's going to be a value of 2 to the south, right? We can just do it with a picture like that. Now, if we wanted to do it with our math skills, that's no problem. Let's pick our directions first. I'm going to choose north and south, obviously, and I'll choose north as positive and south as negative. So any north numbers are positive, south numbers are negative. And I'll say, what's my resultant vector? I'll use R to represent my resultant because I don't know what it is a velocity or force or whatever. So I'll just use R to represent resultant vector. We've got 10 newtons north, so I'll represent that as a 10, positive 10 because it's north. And now I got to add my other vector. It's to the south though, so it's going to be negative. So I'm going to write negative 12. Let me try that again. Negative 12. There we go. Okay, so 10 plus negative 12, that's just negative 2. And what is negative 2? I know negatives are to the south. So now that we've done our math, let's reintroduce our directions here. We'll say it's 2 to the south. I'll put a box around that because that's my final answer. That's how I want to see final answers. Nice box around them to show what's going on. Okay, here's our next one. 22 east minus 8 west. Let's remember that when you're subtracting a vector, you're turning it around. So the first thing we can do is write the equivalent. That this is going to be 22 east plus 8 east. I can change west to east and minus to plus. If I change the direction, I change the sign. Okay, so that's how we can rewrite this, right? Now let's draw a picture. This would be 22 like that to the east, and then another 8 to the east. And you add those together and you say, okay, that's easy to figure out. When you add those together, I started here and I ended over here. That's going to be 30 to the east. Let's do it kind of in our mathy way though, right? We'll say choose our directions. I got east and west. We'll call east positive and west negative. Now the right side of my tablet always has a little bit of trouble here. So bear with me if my writing gets a little funky. So I'll say my resultant is going to be 22. And now I could add the 8. And I'll say, all right, that's a resultant of 30. Another way to do this, I could have not changed my value at the beginning, and I could have said 22, and then I'm subtracting 8, but I know it's going to be a negative because it's to the east. That would also get me to 30, right? So two ways to look at my same problem here. So we'll say, okay, our resultant is 30 to the east because it's a positive value, and I know positives are to the east. Let's put a box around it. Okay, so that's one-dimensional motion, right? We can sketch it. We can give directions of which one's positive, which one's the negative, add or subtract our numbers. We're good to go. Let's try going two-dimensional at a right angle. What we're going to use for this, again and again, is the Pythagorean theorem, which works for any right angle triangle. And it's almost always in situations like this going to be a tangent ratio. Why tangent? Well, we remember good old SOHCAHTOA, right? The TOA part of SOHCAHTOA is opposite and adjacent. So our opposite and our adjacent sides are the ones that are going to show up when we draw this triangle. We usually won't know the hypotenuse. So tangent ratio is going to be our friend in this situation. Okay, so let's have a look at this case. We've got 11 north plus 17 west. Now, what are these units? I don't know. Could be momentum or velocity or force or displacement, whatever, doesn't really matter. Let's sketch out what this is going to look like, right? So I'll get some nice arrows here. Let's do my arrows in nice rich purple colors. So I got, first of all, 11 north. I'm going to draw it just kind of like that. And then I got 17 west. I'll put it in, and it's going to be a little longer than the 11. I'm going to draw it like that. And I think I got pretty close to making this a right angle. Maybe not perfect, but it's just my sketch, right? So I got an 11 north, and then I got a 17 west. Now my resultant, right, is going to be over here, and my resultant is going to start at the beginning and end at the end. It's going to look like that. And I can use a R for that to represent my resultant because I don't know what units it's in. So I would use a V if it was velocity, et cetera, et cetera. And I also don't know the direction. So I would need to find out that angle right there, that angle theta. Let's see if we can figure that out. Okay. So first of all, let's do the magnitude, right? Let's figure out the magnitude. Magnitude, I'm just going to need Pythagorean theorem for this. So I'll say, okay, Pythagorean theorem tells me the hypotenuse squared is equal to the two other sides squared. So r squared equals 17 squared plus 11 squared. And I want to know the magnitude of r, so I'm going to take the square root of both sides. That means r squared is the square root of 17 squared plus 11 squared. That's the square root of 490. So square root of 490 is 20.24847. I'm going to put in a lot of decimals there. Now let's round it off for significant digits. Well, we'll do that at the end, actually. I want to do the angle first. So we got magnitude. Now let's do the angle. And for the angle, I'm going to say, okay, I'm looking at this right here, right? And I notice I know the opposite side and I know the adjacent side. So opposite and adjacent means tan ratio. So I'm going to say tangent of that angle theta is the opposite side over the adjacent side. So that means tan theta is going to be 17 over 11. So theta is going to be the tangent inverse of 17 over 11. You could write that as a big long decimal, but I'm just going to plug it into my calculator like that. So let's make sure we are in degree mode, not radian mode. If you're taking a math course as well right now, you're probably using radian mode a lot. We want to avoid that mix-up. We're all just going to use degrees in this course. That's going to be 57.0947 degrees. Excuse me. Now let's write our final answer for this. So we'll say, okay, our resultant is going to be equal to, let's round this one off. It's going to be, looks like two significant digits because that's what my input data was. How do I write 20 with two sig figs? I'll use scientific notation for that. So I'll write 2.0 times 10 to the 1. And then now my direction, looks like my direction is going to be north 57 degrees towards the west. I'm going to put a box around it. Nice. Okay, for my other one, I think I want to do this on a new page so I don't have that problem with the right side of my tablet getting all funky on me here. So I'm going to grab this one and move it over with us to the next page. Actually, what I'll do is I will just clone this page. There we go. Okay, and now I can grab it and just move everything over like that. Lovely. Now we'll be able to work from this clean canvas. All right, so we got 26 east minus 19 south plus 4 west. I can clean this up, and the best way to do that is to start by writing all your negatives as positives, right? That'll help prevent any mistakes. Instead of having to think about this one and saying, oh, I got to draw it backwards, let's just do it right here. So we'll go 26 east is still good. Now we'll go plus 19, and instead of south, I'll change it to north, right? Because I can change the sign, the direction, and the sign. Plus 4 west. Now everything is pluses. That's nice and easy. That's going to make it easier for me to draw. Okay, so let's get our vectors going here. our first arrow is going to be, and again, we could do this in any order, right? Because they're all pluses, so whatever we want to do is totally fine. We'll do 26 to the east like this. And then we're going to do 19 north, kind of like that. And then we're going to do 4 west, kind of like that. We'll say, okay, our resultant vector is going to start at the beginning and end at the end. It's going to look like that. Okay, let's put in a few other things here. I'm going to put in right here just a little line to demark this, right, to help make this a little easier. In fact, I think I'd like that to be a dotted line now that I think about it. There we go. Much better. It's not quite straight up and down, but it'll do for our purposes. So I said this whole thing on the bottom is 26, but this part is 4, right? So if the whole thing is 26 and that part is 4, this part has got to be 22. This part is 19 because this part was 19 and this part is 4. So I noticed this is a right angle triangle. I can just use my my normal trigonometry to figure this out. I want that angle there, and I want my resultant vector right there. I got to figure that out. So let's do like we normally do. First, let's figure out our magnitude. And so we'll say, okay, r is going to be equal to the square root of 22 squared plus 4 squared. That's just Pythagorean theorem, right? So we end up with 29.06888. Now let's do the angle. And for the angle, we'll say, okay, again, I'm shortcutting this a little bit because we've already seen it. We're going to be tan inverse, and I'm fine with you doing this once you get comfortable with it. Tan is opposite over adjacent, so for my angle, 19 is opposite, adjacent is 22. It's going to be 19 over 22. And I work that out, and I get an angle of 40.81508 degrees. And notice I'm writing 5 decimal places. I'm in the habit of doing that because when I round off, I want to have confidence that I'm not rounding off improperly. So 5 just means I know I'm going to be well past where I need to be, given there was only a few significant digits. Now you'll notice in my question here, right, there's 2 significant digits, 2 significant digits, 1 significant digit. So I'm going to round off to 1 significant digit for my final answer. So my final answer is, okay, my resultant vector, 29 rounds to 1 significant digit of 30. And my direction was 40 degrees. Is it 40.8? I have to ask, is that closer to, like, what's that closest to? We say we'll round it off to 1 significant digit would be 40. So I'm going to say east 40 degrees towards the north. There's my final answer. Okay, let's look at case 3. This is where things start getting a little tougher. Two-dimensional non-right angle. So we can't use SOHCAHTOA anymore. They don't work. What tools do we have left in our toolbox? Well, you're going to be pretty familiar with math class from sine law and cosine law, right? Those are old standbys, sine law and cosine law. Now, I want to warn you, this week I'm going to teach you a technique called vector components. We're going to use that because it is much more powerful than sine law and cosine law. Sine law and cosine law only work when it's a triangle. That means add 2 vectors together and want to find the resultant. That makes a triangle. Yes, they work. But if you add a 3rd vector in there, all of a sudden, with your resultant, that's 4 sides. It's not a triangle anymore. And cos law and sine law do not work anymore. So cos law and sine law, because you're familiar with them, I'm going to show you how they would work. And then basically we're going to abandon them and say these tools are not good enough for what we want to do. We need something better. We need something more powerful. We need something that works in every situation. And that's going to be vector components. So stay tuned for that. Okay, but cos law and sine law are ones we've seen before. We're used to them. If you need some tuning up on this, I'll have posted a video with like some extra stuff on that. So you'll have a little extra practice with that, and you can check it out if you need it. If you're comfortable with those, great, you're good to go. No worries. Okay, let's do our resultant vector. We've got our chickadee here, right? And the chickadee is going to be flying around and it flies. Horizontal plane just means we're looking from above. Down at this is flat. So fence post at P, to a bush at B, and then to a feeder at F. Find a resultant displacement vector. So we're going to start right here. Our resultant will go like that, right? Start at the beginning, end at the end. And we'll say, okay, we're going to call our resultant vector displacement. So we can call it delta D in this case, right? Because we do know it's displacement. Let's see if we can figure out a few more of the angles in here. I'm going to extend this dotted line. And I say, I know if this one down here is 33, Z pattern tells me this one up here is also 33. Those have to match. And I know I can figure out this little one right in here, right? Because I can say the whole thing is 180, subtract out the 28 and the 33 and see what's left. So I'm going to call that angle B, and that's going to be 180 total minus the 33 minus the 28. We say, okay, that's going to end up being 119 in there. So that's 119 degrees right there. Now we look at this and we say, which law are we going to use? Well, cosine law works when we know, let me get my highlighter out, works when we know a side, an angle, and then a side, right? Which we know, 22 meters, 119 degrees, 11 meters. So cosine law will work in that situation when we've got side, angle, side. So we'll say, okay, let's use our cosine law. Cosine law. Here we go. Cosine law is going to be set up like this. We'll say the big side we're trying to find squared is going to equal one of the other sides squared plus the third side squared minus 2 times that one times, that should be a 22, times the cosine of the angle, 119 degrees. And we know that the side we're trying to find and the angle that we're using are opposite one another. That's how cosine law will work. So I work all that out, I crunch my numbers. I'm not going to go through all the math for that because it's not hard math. We're going to save ourselves some time and go 9.7668. That's how big that side is using cosine law. Now I need to find a little bit more information. I need to find an angle inside the triangle, and that's going to be the angle at P. Let me use my highlighter again. I'll do this in green. I'm trying to find this angle right in here, right? So I'm going to call that angle P of the triangle. That's what I want. So I'll say, okay, let's use sine law for that. So we'll go sine law. And for sine law, we're going to say sine of an angle, that would be angle P, over a side, which is opposite, we know is 11, equals the sine of a known angle, 119 degrees, over the side that's opposite that, which we calculated was 28.97668. So we've set up our sine law ratio. Let's solve for this. We'll say sine P is equal to 0.33202, and we'll solve for P by saying what's our sine inverse of 0.33202. See what we get for our angle. It's 19 and a bunch, 39138. So we say, okay, that's what that angle is going to be in there. Now we want to describe this with direction related to north, south, east, and west. So let's take a moment to think about it. So here's the thing, right? We're trying to describe this red dotted line. We're trying to describe the magnitude and the direction of this red dotted line. That's our resultant vector. So I don't want that angle that I've colored in green. I call that angle P. I don't really want that one because it's just in the middle of nowhere. It's not next to north or east. So it'd be easier if I could describe my angle in relation to the east. So if I can get the blue dot I put in there, if I can get that angle, that would work much better for me. So that's what I'm going to try and do. So let's go. Let's grab our pen here and let's say, okay, um, give me a little more space. We'll say, okay, that blue angle in there, let's see, the whole thing is 30, get out of here, highlighter. The whole thing is 33 degrees, but I got to subtract off the 19.39138 that I know is that green part in there, and I'm left with 13.60862. That's the angle that I colored in blue. That's what that angle is going to be. And I can reference that in relation to east, which is great. That's what I want. So let's write my resultant vector. Okay. First thing we're going to do is we're going to say our displacement vector is equal to, and what's our magnitude? Looks like rounding it to two significant digits will be 29 meters. Now let's put our direction. It's going to be east 14 degrees north. Now you could write that as north 76 degrees towards the east. You'll notice I rounded off my angle to two significant digits as I did my magnitude. Both of those need to be rounded off. Okay, so we've solved one. Now this one had units. This was a displacement one. My next one's going to be a little trickier, but I'm going to take the units out again so we can kind of start from scratch and go a little easier. We've got 46 north 80 degrees west, and then we've got 117 south 40 degrees west. Oof, this is going to be vectors at two weird angles, and we don't even have a drawing to work from. Okay, in order to make our lives a little bit easier, I have made these little like compass things. We got a north, south, east, west kind of thing going on here. And I'm going to draw my vectors from here. This is going to make it a lot easier for me to see what kind of angles I'm working with. All right, so let's try and use these as a base to draw our vectors from. So my first one says north 80 degrees to the west. So I'm going to move down here because I know I'm going to be going north and to the west. So let's get an arrow here to represent a vector. And I'm going to start at the beginning and I'm going to go here. Now, north would be straight up and down, but I'm 80 degrees towards the west. That's not the whole way over. It's only 80 degrees over. So it's going to look kind of like that. And it's 46. I don't want to make it too big because the next one's got to be 117. So I'll put it right here and start it right at the center of that thing, and that looks pretty good. Maybe I need to bring it down a little bit because it is 80 degrees. That's almost the whole way down. Okay, so let's do a little bit of writing on here. I'm going to say that this angle right in here is 80 degrees, and I'm going to write really small so I can make it all fit. And I know this one in here is going to be 10 degrees. Okay, and now I'm going to grab this other one over here, and I'm going to put it at the end of this vector because that'll make it easier for me to draw the next one, doing tip-to-tail vector addition. Okay, so here we go. Let's start here, and we're going 117. So that's like 3 times as long, and it is south, like that, 40 degrees to the west. So not halfway over, that would be 45. So 40 is like around like something like that. So there we go. I think that's about right. Okay, I've drawn my vector in there. Let's see if we can add in some angles into this one here. Okay, so I notice I went south and then I went 40 degrees towards the west. So I can say that's 40 in there. And that helps me because I know this one's got to be 50. And can I get this other angle in here, right in here, right? Can I figure out what that one is? And I actually can. I know that this one's got to be 10, right? Because of my Z pattern, because I got a 10 over here. So that means, okay, this one's got to be 90 minus 10 has got to be 80 degrees in here. So I can add these two together. The 40 and the 80 will make a 120 degrees for this whole angle inside here. Now, what's my what's my triangle going to look like? Let's get my resultant vector in there. I'm going to start at the beginning. I'm going to end at the end. There's my resultant vector looking like that. I have my triangle now. I'm going to use my r squared for my resultant. And I'm going to say resultant vector right there. Not sure what it is. We'll have to try and figure it out. I would like to get this entire angle in here. We're going to call that theta because I'm going to want to be able to describe the direction or this angle. And if I had that whole angle and I subtract 10 from it, I'll have this angle right in here. And that would allow me to say how far below west I am. So that's kind of what I want to know. There's a lot of moving parts here. Let's also label this as 46 and this is 117. Okay, let's go to it. The math is actually not that crazy, so let's just jump in on that part. First, let's do our resultant. We're going to use the cosine law. So my resultant squared is going to be the two other sides. It's going to be 117 squared plus 46 squared minus uh, minus 117. Ooh, let me rewrite that. Minus 2 times 117 times 46 times the cosine of the angle, which we know is 120 degrees. Okay, now I'm going to be a little zippy here with the math. We're going to say that r squared is 21,187, and that means take the square root of both sides. R is going to be 145.555755. Now, let's use the sine law. That was the cosine. I guess I should have had a little title up here. Now let's use our sine law. And using sine law, I'm going to match up sides and angles. So I'm going to say I want to know this angle I called theta. So I'm going to match it with the side that's opposite. That's 117. And I know one angle, it was 120. So I'll put sine 120. And that's across from the resultant side, right? And I calculated that. It was 145.55755. So I've done my matching there. Okay, so I'm gonna like rearrange all of this. We're gonna multiply the 117 over. We're gonna take the sine inverse of this, and we're gonna end up with an angle of theta equals 44.11623 degrees. Now I say, okay, that's the whole angle. Let me get my highlighter out here and say, that's this entire angle in here. And I know that that angle is made up of the bottom chunk and the top chunk. I know the top chunk is 10 degrees. So the bottom chunk has got to be 10 less than that, right? So the angle I'm looking for is going to be 10 less than that. That's going to be 34.11623. So I say the angle I'm looking for is 34.11623. So I'll say, okay, my resultant vector is going to be round to two significant digits, 145.55755, rounds to 150, and the direction is going to be to the west, 34 degrees down towards the south. And that's my resultant vector. That's how I describe that. Okay, that's it. So we've done case one, linear stuff. Case two, 2D stuff, right angle triangle, where we use Pythagorean theorem and tan ratio. Case three, things at weird angles. We can use sine law and cosine law, our old friends, to help us out here. Next, in lessons this week, we'll learn how to use the much more powerful vector components. Okay, now it's time to practice. Good luck. I hope it goes well.